Next up, we are going to flip to talking about from tools to exploits. So round of applause for Paweł, who's going to be talking about privilege escalation via Traceroute6. Woo.
Hello, everyone. Set user identification bit. It has let us run programs with elevated privileges since early 70s. It even has a patent from 79. Making it the only patent that came out of research Unix. And this setUID mechanism was used for exploits for probably as long as people have been writing exploits. And with my research, I wanted to check how hard would it be to get root on a modern system like macOS via this mechanism. So this presentation is from zero to the exploit kind of a story, and along the way, I will show you a few bug patterns, a new exploitation technique for macOS default user space heap allocator, libmalloc, and a lazy way to bypass pointer authentication for local user space exploits. I'm Paweł, I'm from Poland. I used to play TFs for Just Cut the Fish team, and I work for Trail of Bits company. The research started as usual with finding the target. There is only like 16 setUID root programs on macOS. I started reverse engineering them. Then I realized that Apple actually open source most of this code, which was super surprising to me, but they do. And after some time, a piece of code in Traceroute utility caught my attention. Traceroute is like that well-known network utility that shows network paths to some hosts. And this is the interesting function simplified. You can see the domain of 256 bytes, and there's a getHostByName function is called from the standard library, and resolved domain is copied to the allocated buffer, and there are no overflow checks. So I figured maybe the getHostByName function may return more data than it should, and let me try to show that on like the virtual machine. Of course, it won't work. So I guess whatever. I can show the demo. So what I did, I put a lot of A's into the etc host file and ran traceroute, and it crashed. And this is only a SIG trap, not segfault. So it's not exploitable because of that 40 source mitigation. But I wonder why the overflow is possible in the first place, because the DNS spec mandates you that the domain names should not be longer than these 250 some bytes. So I went into the getHostByName function to check how it works. It calls into a libinfo library from Apple, and that library has multiple modules that try to resolve the domain name. So there is a cache, there are a few that are not used on macOS by default. Then there is the file one and the mDNSResponder one. So the flat file one just reads from the etc host without any validations, so no wonder that crash happened. Next thing I wanted to check is whether the mDNS module can be like abused to trigger the crash remotely from remote DNS server. So the mDNS module does not talk with the remote servers directly. It talks with a local DNS daemon over Unix domain socket. And simplified code of the module is that it loops over all DNS responses, reading data from the socket onto the heap, then parses the data. And there are few fields in DNS response. There is that name, type, class, record data, time to live. And the interesting one to us is the first one, the name. And it's limited by service max domain name constant. And that constant is 1008 bytes, which is kind of surprising. And why is that? So domain names can be represented in a few ways. You can have like the human reliable representation, and there is the Unicode encoded representation that I think is not standardized. It's internal to Apple, probably. And there is the wire format, where you have subdomains prefixed with 1 byte length. So theoretically, the client may read up to 1008 bytes, so theoretically could trigger the overflow remotely. However, the thing is that the daemon will never send a Unicode encoded domain back to the client. It will always send the domains in wire format. So this is probably like a bug in the client, I know. Anyway, it wouldn't be exploitable. So the next thing I wanted to check is whether we can make the traceroute somehow communicate with our exploit instead of the daemon. And surely enough, it's easy to do so. It was easy to do so. We just need to run the traceroute with this envar, and the path of the socket will be as we choose. And with that, we increased attack surface from only the traceroute to also the whole DNS client stack. And with the new attack surface, I did some fuzzing and then found a bug in parse domain name function. So the function takes as input record data len and r data pointer that points to our buffer. What this does is it tries to parse the wire format DNS representation into human readable representation. Note that the RDLAN is casted to uint 4 bytes integer. On the left, you can see the input. So there's the RDLAN, the input domain, r data pointer. There is time to live, and some garbage data, whatever we send. What that function does is it iterates over all the data, reads the length byte, allocates output buffer called domain, and then goes into inner while loop. And the inner while loop, it copies all the whole subdomain. And the bug is in that while loop condition. So here we check that len is greater than 0. That is correct. The issue is on the right-hand side of the comparison. And to see the bug, let's assume that RDLAN is 0. So what happens now is that 0 doesn't equal 0 is false. So we break from the inner loop back to the outer loop. However, the decrementation is still executed. So RDLAN will overflow from 0 to uint max, so to a huge number. And with that, the function will keep iterating over time to live, over whatever data we have sent after that. In itself, it's not like exploitable issue. However, take a look here. The J variable is used as offset to the output domain buffer, and it is a signed integer. So if we can make the function iterate a lot, like a lot, the J index will eventually overflow too into a negative number. And we'll have a pretty nice heap buffer underflow kind of vulnerability to exploit. Like getting domain parsing from wire format is apparently pretty hard because Apple got it wrong. And also the famous Loft group got it wrong in 2000, and they have that kind of famous bug in their anti-sniff tool that you can read more about in the Art of Software Security Assessment book. Okay, with that, we need to exploit the underflow. So you can see on the screen the virtual memory mapping of traceroute, only the writable pages. The memory mapping starts with malloc metadata. This is like a global metadata. Then there is the actual heap with a few regions. Then there is stack and some other like pages. Domain is allocated somewhere. We write from 0 to int max. And when overflow happens, we write to domain minus 2 gigabytes. Now on Intel, as you can see, the space between the heap and the malloc metadata is quite large. So the overflow will always end up in the void. And the problem with libmalloc is that it grows upwards from near the stack up to the sky. So because of that, the domain pointer will always be allocated somewhere near the top of the heap. So the overflow will always ends up in the void. So what we need to do, we need to change the heap growth direction. And the trick to do that in malloc is to make the libmalloc allocate a lot of data. Like my exploit use 8 gigabytes, and then freedol. And now for 8 gigabytes worth of allocation, the heap will grow downward. And with that, the domain is somewhere near the bottom of the heap, and the overflow will end up somewhere on the heap. Now, to do that, on traceroute, we need the traceroute to call getHostByName 2 times, one to allocate all that data, then free it, the second time to trigger the overflow. The problem is that just after the first get host by name call, traceroute drop privileges, calling setUID. So I thought bummer, no exploits for me. Then I take a look at Traceroute6, however, and this is basically the same code, except for whatever reason it calls set effective user ID before calling set UID. And this is wrong. And to see why it's wrong, it's that when the program starts, the effective and safe ID are 0. After set effective UID call, only the effective ID is changed. And then set UID thinks, OK, effective and real IDs are the same, so I'll do nothing in return. And the saved ID is not changed. So the exploit can simply call set UID 0 to restore privileges and get the root shell. And if you are thinking that this silly bug, then please take a look at this paper from 2002, where researchers tried to decode the Unix permissions like state machines. Kind of crazy. OK, now we can land the override somewhere on the heap. The question is what to override. There are like two ways to exploit heap, like in general. One is to overwrite application data. However, Traceroute doesn't put anything useful, any useful pointers on the heap. So we cannot do that. And the other way is to use to override the metadata. Problem with libmalloc is that most of the pointers, even libmalloc, are signed with a custom algorithm. And the signatures are only like 4 bits long sometimes. So we could brute force that, but because our exploit is already pretty slow because it has to allocate a lot of data, it would make a pretty lame exploit. So I wanted to find another way, more stable way. And there is a presentation from 7 years old from Synactive. They've researched the libmalloc from exploit development point of view, concluded that there are no generic techniques to exploit that heap allocator. However, they noted that metadata at the end of a region maybe is exploitable, but that's another story, and that story was never told. So that's seemingly it will be happening today. Okay, so what's region metadata? What's region? Region is just one or more continuous memory pages, and that holds allocations of similar sizes. And here you can see we have like 1 tiny regions, 3 small regions, some large regions. And every region starts with metadata. So this is a different thing than this global metadata that you can see on the top. So there is metadata in a region. There is region cookie, which is like random cookie similar to stack cookie protection. And then there is space for the actual allocations that programs can use. And the region starts with these 2 interesting pointers, previous and next. And these pointers turns out to be not protected by the custom signatures. And they are used in the results list extract function. So what that function does is implement double linked list or takes element out of it, whatever. From exploit development perspective, it gives us override pointer with a pointer kind of primitive, if we can call it. And to call it, and that function is called when a chunk is freed. So now with libmalloc, the thing is that if all chunks in a heap are freed, then the whole region is unmapped completely from a memory. However, if a region becomes sparse, so like most of the chunks are freed on the specific region, then it will be moved to a special like magazine called depot, so basically to that double linked list. So for the exploitation technique, it means 2 things. One, that we have to move at least 2 regions into that depot list. And to do that, we need to allocate a few regions and then free most data in that regions, but not all of the data. And the second requirement is, in addition to overwriting previous and next pointers, we have to overwrite some more metadata in a very specific way. Okay, so let's say we were able to override the next previous pointers, execute this function. Now what happens in libmalloc is that there is that if check that is always false because of how we had to set up the metadata. And that means that malloc zone error function is always called just after we overwrote one pointer. And that function is pretty scary from exploit development perspective because it calls simply path and then aborts. And if it aborts, then it's game over for us. And let's see what that simple path function does. It calls flash. Flash calls write syscall. And on macOS, syscalls are wrapped so that if a syscall fails, it will call the error function. And that function calls thread exit if cancelled. And that function calls libkernel functions something. And that's perfect for us because libkernel functions is a pointer that we just before could overwrite. And that means we have one more requirement for the technique. We have to make the write syscall fail so that the error function is executed. Locally, it's trivial to do. We just need to close the terminal. But that means that this technique is only for the local exploits. However, for remote exploits, it's also possible, but with not small region, but with some other regions. But it also makes the exploit less stable. Now we know what to overwrite. We can override the kernel functions. The question is, what is the address? So the kernel functions pointer lives in the libsystem kernel shared library. Now on Unix systems and on old macOS systems, shared libraries were located in the file system and loaded into process memory whenever the process started at a random address. However, Apple made that optimization and that platform libraries are now loaded into memory when the system boots. So they are randomized only once per boot. And that means that the exploit can find the libsystem kernel functions pointer in its own memory, and it will be the same address that trace it use. This is like super cool optimization from Apple for local exploits. Okay, we know where to write. The question is what to write. So we need to override that pointer with pointer to heap because we control data on the heap. And the question is, so we have to find the addresses of the heap to do that. And we can do that with the most powerful hacking trick out there. We can run the program with debug equal to 1, and it will just print all the pointers we need for us. Okay, with that out of the way, we can just job, call setuid, execute a shell. However, at this point, before I finish the exploit, I got a brand new macOS with Apple Silicon, so I changed the target. And to see differences between the Intel architecture and Apple Silicon, let's take a look at the virtual memory space again. So the main difference is that the distance between the heap and the global metadata is large on Intel, but it's not that large, it's pretty small on macOS, on Apple Silicon. That means three things. One is that our exploit needs to do less heap spraying. In general, it means that in addition to this regional metadata overflow technique, one can also try to actually land the underflow onto that global metadata region somewhere. Also means that libmalloc is kinda not well optimized for Apple Silicon because it tries to grow the heap upwards, but on Apple Silicon there's limited space for that. Okay, so the bigger problem that I learned about on Apple Silicon is pointer code authentication. It was already mentioned a few times, like yesterday. So this protection, this mitigation works that a program can use new assembler opcodes to sign pointers. The system has a few keys, and it will sign pointers for you. And then when traceroute or some program wants to use the pointer, it will use a special assembler opcode again, and the system will do the verification, and the program will be killed if the pointer is wrong. Now, libmalloc does not use PAC yet. It has the custom signatures. However, the libkernel functions uses pack, so we have to bypass that somehow. And the key observation for the bypass is that all programs signed by the same team will have the same pack key. That means that all platform binaries like sudo on traceroute, but also like vim and ls and probably some like local Apple services will have the same pack key. And so the idea was to get any Apple program and make it a pack sign pointer for us. I tried to use like Bash or Python, like programs that are expected to execute arbitrary code, but GNU disables pack altogether for that selected programs. Next trick is the LD preload trick, but if you take like random binary from Apple and try to inject a shared library, it probably won't work because there are like many different protections. However, there is a lot of Apple binaries out there, so the idea was to simply find any Apple signed binary and that has all the protections turned down. And truly enough, there is at least one such program. It's called Remote Virtual Interface Tool. I have no idea what it does, but when you run it with that envar, it will just execute code for you. And because it has the same pack key as traceroute, we can just use it for the pointer signing. Okay, I can show you like demo from recording because I cannot get my VM on the display. We're in Python. Python prints some data, and the exploit takes a minute, so like whatever. It prints more data, blah, blah, blah. And we will get root at the end, like crazy stuff. You can find the exploit code at Trail of Bits GitHub, and you can demo it for yourself if you like really need. Anyway, this pack bypass seems still to be working, unless Apple changed the key management in GNU. I don't think they did, but maybe. It has some constraints, like only the code keys are shared, the data keys are not, and some like very sensitive application may like opt in to get unique A keys with that special entitlement. Okay, so to sum up, 1 to 3 bug patterns for you, and the libmalloc regional metadata exploitation technique, and that lazy way to bypass pack. And I wanted to thank you, Disconnected, for help with the exploit, Tom for being my mentor, and Apple for the bugs and the bounties. Thank you.